Okay, so good evening everyone. I welcome you all for the week 9 tutorial of this course of Principles of Signals and Systems. And yeah, okay, so like every week's tutorial, we'll first discuss the content that was covered in this particular week, followed by the questions that are related to this particular week's content. If you have questions at any point of time, please feel free to unmute yourself and ask. Refrain from using the chat box because it might not be visible to me throughout the tutorial session. You can unmute yourself um, at any point of time and stop me to ask the questions. Okay, so let's quickly start with the recap of week 9 content. Give me a moment. Yeah, okay. Okay, so in this particular week, we first continued our discussion related to the ideal low-pass filters, and then we looked at the actual implementation or in practice how these will be implemented. So we said that an ideal low-pass filter will potentially, one second, yeah. So an ideal low-pass filter has a frequency domain representation, something like this. So it passes your signal completely for a particular band of frequencies, let's say between your omega c and minus omega c to omega c, and otherwise it just does not allow any other frequency to pass through. This is an ideal filter. This is your ideal low pass filter. What do you mean, what do you basically mean by ideal low pass filter? If you see, this particular band here is known as pass band because it allows passing of these particular set of frequencies. And this particular band is known as the stop band. And there is a sharp transition between the pass band or stop band. Or in other words, the frequencies that or this transitioning between your pass band and stop band does not occupy any band, or there is no transition band. Such a filter is ideal low pass filter. Furthermore, the amplitude of your filter in the pass band is 1. It is 1. And in stop band it is 0. Again, this is not possible to achieve in practical scenario. You will have certain pass bands magnitude. You will get something like this. So you will have a significant amount of magnitude available in the pass band. So let me be clear here. This pink one is your ideal low pass filter, and this blue one is your practical one. So if you see, if this particular thing is your pass band, so this particular band corresponds to your transition band. Okay, and there is a non-zero transition band that will be present in the systems, practical systems. And how do you construct these practical low-pass filters? So typically those are constructed in using RLC circuits. And a typical example of your RLC based low-pass filter we saw in the class was your RC filter. So this is particular thing that we saw. Sorry. Yeah. This is an example of a circuitry that allows you to construct low-pass filter. This is a very basic way of constructing your low-pass filters. Now, in the context of RC filters, we looked at different things. We looked at 3 dB cutoff frequency. Then we looked at something known as RLC, rise time. So first thing that we looked at was omega 3 dB. What do you mean by 3 dB band? So this is 3 dB cutoff frequency. We saw a few examples of this 3 dB cutoff frequency, how to obtain it in the previous lecture, but I'll just write it down here. So at this particular frequency, the magnitude of your filter filter transfer function is half. So if you convert half to a decibel scale, it corresponds to minus 3 dB, and because of that, you get a 3 dB loss. If this particular magnitude is 3 dB, or let's say I'll just write it something like that. So this is for the particular value of frequency at which you see a 3 dB degradation in the magnitude of your transfer function of your filter. That's why we name it as 3 dB frequency. We saw a few examples in the last class. I don't want to repeat those things in this particular thing. And the other thing that we looked at specifically in this particular week was something known as the rise time. What do you mean by rise time? So rise time is the time taken by the output to increase from 10% to 90% of the final value. And we saw that for this particular RC circuit, when you give unit step function as your input, this rise time, this is very specific for a particular setup. This is not a generic formula. Is RC into natural log of 9, which is almost equal to 2.1972 RC. And we also saw its relation with respect to your cutoff frequency, and we saw that the 3 dB frequency was essentially 1 by RC. Therefore, this corresponds to 2.1972 upon 2 pi f3 dB or omega 3 dB. This is equal to 2.1972 upon 2 pi f3 dB. This is all about filtering that we saw in this particular week. After that, we switched gears, and so after that, what we want to do is we want to study discrete time signals. But if you see, all the signals that are naturally occurring are continuous time in nature. So therefore, first we need to understand how to move from continuous time to discrete time. So that is achieved by something known as sampling. So sampling of continuous time signals basically moves you from continuous time domain to discrete time domain. And then we saw the very basic or very crude way of doing sampling, and that is through impulse train sampling. So how do we do that? We do that in this particular fashion. So let's say you have a time domain signal which is showing something like this here, and let's say it is a band limited signal with maximum frequency as little omega n. Okay, you have this particular setup, and now you want to sample. You want to sample this continuous time signal to get a discrete time signal, and to do that, what we do, we multiply this x of t with an impulse train delta ts of t, such that you have a unit impulse at every integer multiple of ts. And what is ts? Ts is basically your sampling duration. So ts is your sampling duration, and 1 by ts, that is your fs, is your sampling frequency, and In angular frequency domain, you will get 2 pi fs is equal to omega s. This is your angular sampling frequency. Okay. Okay, so at every integer multiple of your sampling duration, you have a unit impulse. And then you multiply this xt by this train of impulse, which gives you something like this. So what does it do? This unit impulse picks up the value at that particular location. For example, at t equal to 0, this particular thing has x of 0. This particular impulse has an area of x of ts. This particular thing has an area of x of 2ts and so on. So what you basically do, you multiply your signal with train of impulse to get again a train of impulse but with different magnitudes, and that magnitude is governed by the signal amplitude at that particular location, and this is basically your x of nts which is basically your x of n. X of n is your discrete signal coming from our excess of n. Yeah, sorry. Yeah, this one. Okay, so this is how you sample. So now what happens to its corresponding frequency domain representation. So we saw that this particular signal x of t has a Fourier transform as x of omega, and let's say it is a band limited signal with maximum frequency as omega m. Then we have this train of impulse, and we have seen it multiple times. We have first seen it in the last lecture, and we have also seen it in the class that a particular train of impulse, the Fourier transform of that will again give you a train of impulse. So that we had seen earlier. So now we get a train of impulse whose magnitude is omega s, and it is located at every integer multiple of your sampling frequency. Now, what we do, we multiply this x of t with this delta ts of t. So you get x's of t as x of t into delta ts of t. Now, when you want to find out the Fourier transform of the signal x of t into delta ts of t, that will give me the frequency domain, the convolution like this. Okay, so you get a convolution of what? Of this particular signal, this particular Fourier transform x of omega and this particular Fourier transform. And when you convolve a particular signal with impulses, you get the replicas at each and every location of that impulses. So you get replica of your x of omega at every location or every integer multiple of your sampling frequency. That is your x's of omega, where you have x of, where the magnitude of this will be x of 0 by ts. So this also we saw. Now, okay, you sampled, you did your processing, you did everything, and but now what you want to do, you want to recover back your analog domain, your continuous time signal. So how to do that? So if you closely observe your original signal, this Fourier transform, this one and this one, this and this is common. The additional parts are located at every integer multiple of your sampling frequency. So in order to get this particular Fourier transform back, I can pass this particular thing through a low pass filter such that its cutoff frequency is more than, cutoff frequency omega c is more than omega m. And this particular signal, since I want to cancel out this ts, will have a magnitude of ts. Now the inverse Fourier transform of this is a same function that also we have seen. So now what you do, this xr of t basically is excess of t convolved with your h of t, and that gives you impulses located at every location of your sinc functions located at every location of your impulses. And then we take into account our envelope of this particular thing to retain back our original signal. So now this is possible only when these replicas do not overlap. But If those replicas overlap, you get a situation which is something like this. So what is happening? So this is your omega m, this is your omega s minus omega m. So if your omega s minus omega m is less than omega m, or in other words, your omega s is less than 2 times omega m, then no reconstruction. So you can't reconstruct. So if even if you pass this particular thing through a low pass filter, the Fourier transform that you will be retaining will look something like this, and which is not equal to the Fourier transform that you have, or Fourier transform of your actual original signal. So you can't reconstruct your original signal by when you have such overlaps, and such overlaps are known as aliasing. Okay, so this particular aliasing phenomena and all those things give you a constraint on the sampling frequency when you have a band limited signal, and that essentially gives you something known as your Nyquist sampling theorem. So I'll quickly write it down. So once 1 minute. Okay. Yeah. Okay. Huh. So this particular discussion, whatever we just did, gives you a very important theorem in the context of signals and systems, or even any field related to signals and systems, and that is known as your Nyquist sampling theorem. And what does this theorem say? So let's say x of t is a band limited signal. This band limited is a very important term. So let's say x of t is a band limited signal with maximum frequency as omega m, then x of t can be uniquely recovered from its sampled version if the sampling frequency omega s satisfies the following condition. So your sampling frequency omega s should be at least equal to 2 times the maximum frequency, or 2 times your omega. So this is your Nyquist sampling theorem, and once you sample it properly, you get your discrete time signals, and then we are good to go to do discrete time signal processing. In order to do discrete time signal processing, the first tool that we looked at was the frequency domain representation for periodic discrete time signals, and that is given by your discrete time Fourier series. So what does it say? So let's say your x of n is a discrete time periodic signal with period, or to be specific, with fundamental period, and naught. Then the fundamental angle of frequency, let's say omega naught, is given by 2 pi by n naught, and then we said that similar to your continuous time Fourier series, we can represent this the discrete time signal x of n as a linear combination of ck's into e power j times integer multiple of the harmonics, integer multiple of your angular frequency, which are your harmonics. So e power j times kth harmonic into n, and you can obtain these ck's using 1 by n naught summation n in any range of your n naught x of n into e power minus j k omega naught n. So this is your discrete time Fourier series representation, and we saw this in the lectures, and we looked at four properties of this discrete time Fourier series. There are other properties also, like linearity and all those things, they follow as it is. The first thing that we saw was convergence. When does when does ck's converge? So if you observe carefully, the ck's are basically finite sums. Convergence comes up when you have an infinite summation. So this is basically a finite summation. It's a summation, not an integration over a finite duration. It's a summation, so it is always guaranteed to converge. So this is guaranteed to converge. And why? This is because you have a finite sum or finite duration sum. And then we saw another interesting property of your Fourier series, discrete Fourier series, that your Fourier series coefficients are periodic. And with what period? They are periodic with the same fundamental period as your original signal. So your Ck plus n naught is exactly equal to your Ck. So your Ck's are periodic with period n naught. Then we looked at another interesting thing, that is duality. So let's say x of n has Fourier series coefficients ck. Let's say it is also denoted as ck, c of k. Then if you take ck's in your time domain, that is, let's say you have c of n, then this will be the Fourier series coefficients of this particular signal will be n naught times x of minus k. So this is the duality property of your Fourier series coefficients. And finally, we looked at another important property, which is important a lot, is Parseval's relation. And Parseval's relation basically gives you the preservance of power when you change the domain from time to frequency. So what does it say? If x of n has Fourier series coefficients as ck, then your 1 by n naught summation n running from 0 to n naught minus 1 x of n squared. This is exactly equal to summation k running from 0 to n naught minus 1 magnitude of ck squared. So this was all that was covered in this particular week. If you have any questions, then let me know. Otherwise, I'll move on to the numerical questions that I have planned to cover. Okay, if there are no questions, then let's move on. So let's start with the first question that we have. So it says that find the cutoff frequency of the ideal low pass filter such that it passes exactly k%, where k is in 0 to 100, of the energy contained in the signal x of t, which is equal to e power minus 80 ut. So what is it saying? You have an input, that is your x of t, which is e power minus 80 into ut, where a is greater than 0. So Fourier transform exists. This is input to an ideal low pass filter with, let's say, impulse response is h of t and cutoff frequency as omega c. What does it say? So this omega c, we want to find this omega c. We want to find this omega c such that the energy in x of t, or rather k%, or let's say, okay, you have, that will give you output which will be y of t, which is equal to h of t convolved with x of t. So how do you want to choose this omega c? Choose omega c such that energy in y of t is equal to k% of energy in x of t. Okay. Now what is the expression for energy? So energy in x of t, let's say is given by ex. It is integral minus infinity to infinity magnitude of x of t squared dt. Okay. So this we can obtain as integral 0 to infinity, since your x of t is only between from 0 to infinity, e power minus 2at dt. This is equal to e power minus 2at by minus 2a from 0 to infinity. This comes out to be equal to 1 over 2a. Let's say this is the first expression that we have. Now we have this energy in x. We want to find energy in y of t, that is your output also. So how is this obtained? So this e of y is integral minus infinity to infinity magnitude of y of t dt, magnitude of y of t square dt. Now y of t we know is convolution of your h of t and x of t, and h of t being an ideal low pass filter, it is the same function. Again, finding this particular thing in like convolving with sinc and then finding the magnitude square is tedious job. So what we can do? We can invoke Parseval's theorem, and if you do that, this will be equal to 1 over 2 pi integral minus infinity to infinity magnitude of y of omega squared d omega. And this comes from what? This comes from Parseval's theorem. Parseval's theorem for Fourier transform, continuous time Fourier transform. And we know that if y of t is convolution of h of t and x of t, then the Fourier transform of y of omega is basically h of omega into x of omega. And h of omega is what? Since it is an ideal low pass filter, it is equal to 1 when your omega lies between the cutoff frequency minus omega c, and it is 0 otherwise. So this is what you have. Then y of omega, which is h of omega into x of omega, is what? It is equal to x of omega when omega lies between minus omega c and omega c, and it is 0 otherwise. Okay, so now let us plug in whatever we have in this e of y. So therefore e of y is 1 over 2 pi integral. This y of omega is non-zero only in the range of minus omega c to omega c. So minus omega c to omega c, and in that range it is equal to magnitude of x of omega squared d omega. This is equal to, okay, so we have this, let's say this is equation number 2. So we now have the relation of y of omega and x of omega. Now or energy of in y in terms of x of omega. But now what we need to do is we need to first find out the Fourier transform x of omega. So your x of omega is Fourier transform of your input signal x of t. So this is equal to integral minus infinity to infinity e power x of t into e power minus j omega t dt. And your x of t is what? It is e power minus 80 ut for a greater than 0. So it is 0 to infinity e power minus 80 into e power minus j omega t dt. We have solved this 100 times, but still let's do it. 0 to infinity e power minus t a plus j omega dt. This is equal to e power minus t a plus j omega divided by minus a plus j omega from 0 to infinity, and this will give me 1 upon a plus j omega. But we are not interested in x of omega, we are interested in magnitude of x of omega whole square. So using this, whatever we just derived, your magnitude of x of omega whole square is basically 1 over magnitude of a plus j omega whole square is equal to 1 upon a square plus omega square. So now let us plug in these things in your equation 2. So therefore, from equation 2, Ey is equal to 1 over 2 pi integral minus omega c to omega c upon 1 upon a square plus omega square d omega. Now this 1 over a square plus omega square is an even function, so I can write this as 2 upon 2 pi 0 to omega c 1 upon a square plus omega square d omega. Now 1 upon a square plus omega square integral is basically tan inverse of 1 by a tan inverse of omega by a. So this is equal to 1 by pi 1 by a tan inverse of omega by a from 0 to omega c. Tan inverse of 0 is 0, and then you get 1 over pi a tan inverse of omega c by a. Now this is what? This is your energy of your output. Now they have given you a relation between your Ey and Ex. So your energy in Y, that is Ey, should be equal to the k% of your energy in X, that is Ex. So what you have, or rather given to you, is what E of Y should be k% of Ex. And yeah, and what are we interested in finding? We are interested in finding omega c. So your E of Y is 1 over pi a tan inverse of omega c by a. This is equal to k%. I can write as k by 100 into Ex is what? Ex we obtained as 1 over a. So this is 1 over 2a. This a here and this a here gets cancelled. So what you get is tan inverse of omega c by a becomes k pi by 200. So therefore omega c becomes a times tan of k pi by 200 radians per second. So this is the cutoff frequency that we are interested in. Any questions? Okay. If there are no questions, then let me move on to the next question. So the next question is pretty straightforward. What it wants you to do is wants us to find the rise time of the RC circuit for the following given values of R and C. So even while discussing today, we saw that the rise time, that is T rise, is given by 2.1972 RC. So we just want to plug in, we just have to plug in the values of your R and C in this particular formula to get the rise time for different combinations of this. What we'll do is we'll see how your rise time changes with the changes in your R and C values. Okay. So let's first start the first one. So for the first one has R as 1 kilo ohms and C as 1 microfarad. So your T rise is given by 2.1972. R is what? 1 kilo ohms. So 1 into 10 raised to 3. And C is what? 1 microfarad. So this is 1 into 10 raised to minus 6. So this is basically 2.1972 into 10 raised to minus 3 seconds. Or this is also equal to 2.1972 milliseconds. This is for the first set of combinations. Similarly, you have the second set for which the T rise is given by 2.1972 into what is the value of your R? The value of your R is 10 kilo ohms. So you have a higher resistance, and let's see your value of your capacitor is same, that is 1 microfarad. So this will give me 2.1972 into 10 into 10 raised to minus 3 seconds, or rather 21.972 milliseconds. So as your R value became 10 times, your T rise also became 10 times. So your system is taking 10 times more time to saturate to do the 90 or to cross the 90% value, from 10% to 90%. And the third one is we have T rise equal to 2.1972. Now let's say we fix the resistance value to 1 kilo ohm, which was in the first part, and now you reduce your capacitance. When you are reducing the capacitance to 1 nanofarad, nano is 10 raised to minus 9, so that will give me 2.1972 into 10 raised to minus 6, or this 2.1972 microseconds. So you reduced your capacitance value by 1000 times. So your rise time also reduced by a factor of 1000. So how does these outputs look like? Let's quickly try to understand that. So you have your output. This is, let's say, your time. And let's say without the loss of generality, the maximum value of this particular signal is, output is 1. So let's say 1 is the maximum value of output. This is your y of t. This is your t. So what is 10% of 1? It is 0.1. So you have 0.1. You have 0.9 as the 90% value. Okay. So this is your 0.9 and this is 0.1. Now let us look at the first value of T rise, that is 2.1972 milliseconds. So your signal output starts from 1. Let's be consistent with the colors. So it starts and then it slowly increases. Then it crosses the 90% value and then it slowly starts to saturate to 1. So this particular value, this one, this duration is your T rise, that is 2.1972 milliseconds. So 2.1972 milliseconds. Then you have another system or another combination of your R and C that gave you 21.972 milliseconds. Now again, whatever I draw is not to the scale. It has to be 10 times, but yeah, consider it will be higher. So it very slowly increases and then crosses your 90% value like this somewhere here. So this one, so should, 1 second, let me change the color of this. Yeah, okay, so you have this, change this, yeah, okay, yeah, like this you have. So now again you have this and you have this. So somewhere here, so this duration, that is from here to here, it is 21.1972 milliseconds. Of course this is not to the scale, but you can assume that, like, you understand that this takes much longer time to move from point 1 to point 9, and the last one that we had was 2.1972 microseconds. So what it does is it quickly goes above point 0.9 and saturates to 1, something like this. So this distance, like this much, this is what? 2.1972 microseconds. So the rise time for your third system was smallest, so it quickly increased and saturated to the final output value, that is 1. However, for your second option, second combination, it took a lot of time to converge to the final output, final value. Okay, so this is all about this particular question. If you have any questions or queries, then let me know. Okay. Okay, then let's move on to the next question. Now let's move on to another concept or important topic that we looked in this particular week, that is sampling, and we'll look at different questions related to this sampling. Okay, so first question here says that let x of t be a signal with Nyquist rate as omega naught. What is Nyquist rate? Nyquist rate is equal to 2 times your maximum frequency. So what is given to us is x of t is a signal with Nyquist rate as omega naught. So 2 times omega m, where omega m is the maximum frequency, is omega naught, or the maximum frequency in x is omega naught by 2. This is given to us. And now what we need to do? We need to find the Nyquist rates for the following signals. And the first signal of our interest, the first signal of our interest is x1 of t, which is equal to x of t plus x of t minus 1. Okay. Then what is the Nyquist rate for this signal? Let's say omega 1 is the Nyquist rate for this signal will be 2 times omega m1, where omega m1 is the maximum frequency in x1 of t. Okay, so this is what we have. So in order to understand what is the maximum frequency, what should we do? We should first find out the Fourier transform of this signal. So let's say the Fourier transform of this signal is given by x1 of omega, That is basically Fourier transform of your x of t plus x of t minus 1. So therefore your x1 of omega will be equal to Fourier transform of x of t plus Fourier transform of x of t minus 1. This comes from which property? This comes from the linearity property of Fourier transform. So let's say this x of t signal has a Fourier transform as x of omega, and the Fourier transform of x of t minus 1 will be given by e power minus j omega into x of omega. This comes from which property? This comes from time shift property. With t not equal to 1. Okay, so these properties you need to keep in mind, otherwise it will start becoming very difficult for you people to understand what is happening. Okay, so now I can take out this x of omega common, then I will be left with e1 plus e power minus j omega. Now from this particular bracket, let's try to make sense of what is happening in this particular equation. It's very difficult to work with complex exponentials, so let's try to bring it to a form that we know. In order to do that, what I will do, I'll take out e power minus j omega by 2 from this particular term. So x of omega into e power minus j omega by 2. If I do that, the first term will become e power j omega by 2. How? So e power minus j omega by 2 into e power j omega by 2, that will give me 1 plus e power minus j omega by 2. So that is the term that you will get. Okay. Now I can multiply and divide by 2. So the first term here, or not the first term, this particular term that I am highlighting is nothing but cos of omega by 2. Okay. So what we get? We get x1 of omega as x of omega into e power minus j omega by 2 into 2 times cos of omega by 2. So this is a Fourier transform, and now we want to understand what is the maximum frequency of this particular signal. And in order to do that, we can simply look at the magnitude. So let's say you have magnitude of x1 of omega, that will be 2 times magnitude of x of omega into magnitude of cos of omega by 2, and magnitude of e power j omega by 2, this is basically equal to 1. So what do we get? We have two terms here. So you have your magnitude of x of omega, which is band limited from minus omega m to omega m. We saw that. And then you get cos of omega by 2. So your cosine function will look something like this. Okay. So cosine function, so it is for all values of omega, it's not band limited. And so on. So you have your thing something like this. Now what your this is your magnitude of cos of omega by 2, let's say 2. Yeah, 2 times. Okay. So your magnitude of x of omega is basically multiplication of these two. So when you multiply these two, what will you get? You will again, so in this particular region, for omega greater than omega m and for omega less than minus omega m, your magnitude of x of omega is 0. So when you multiply this with this particular signal, you will again be restricted in this particular band. So the product will be restricted in this band. therefore, what do we see? We see that the maximum frequency in x1 of omega is also equal to omega n. So what do we see? The maximum frequency which is omega m1 in your x1 of omega is omega m1 equal to omega m. Therefore, Nyquist frequency it is equal to 2 this was omega 1 which is equal to 2 times omega m1 which is equal to 2 times omega m, and we know that 2 times omega m is simply equal to your omega naught. So omega. Yeah. So Nyquist. So if you shift the signal in time domain, that is not going to change the maximum frequency in your signal. So even if you shift your signal in time domain, the same sampling frequency will work out for you. Okay. So shifting in time domain does not change the sampling frequency or the Nyquist rate. Okay. So this was all about the first part of this question. Let's move on to the second part. So in second part you have x tilde t as x square t. Now again let's look at the Fourier transform of this signal. So let's say we take the Fourier transform of this signal, that will give me x tilde of omega. That will be basically 1 over 2 pi. So this x square of t is basically multiplication of x of t with itself. So using multiplication in time property, the Fourier transform of x tilde of t will be nothing but x of omega convolved with x of omega. Right. So this is coming from where? This is coming from multiplication in time property. Okay. Now this convolution is definitely going to change the maximum frequency that is present in the signal. So how does it change? I think we have seen it once, but still let's do it. It's worth doing it. So this convolution, how can we write? We can write it as 1 over 2 pi integral minus infinity to infinity x of lambda into x of omega minus lambda d lambda. So we are interested in what? We are interested in x of lambda and x of minus lambda first. So let's say you have your capital X of lambda is something like this, which is between omega m and minus omega m. Your x of minus lambda will be again the same thing. So this is x of minus lambda, which means this is the case when you have omega equal to c. Okay. Now, when you are convolving these two things, we need to look at the overlapping regions. Okay. So, okay, let me change the color. Sorry. Okay. So this is your x of minus lambda. This is your x when omega equal to 0. When you change your omega to minus omega m, it looks something like this. So this is the case when your omega is equal to minus omega m. Your omega is at 0 here. Omega is at 0 here. So if your omega changes to minus omega m, this is like this. So still you have some sort of overlap. But now if your omega changes to minus 2 omega m, then your overlap starts. So what do we see? We see that the overlap starts at minus 2 omega m. Now again, you are here at omega equal to 0, you are here at omega equal to 0. Now if your omega becomes omega m, you are somewhere here. Now still there is a significant overlap, but when you change your omega to omega when you change your omega to 2 omega m, your overlap ends like this. So what do we see? And the overlap ends at 2 omega m. So how does your Fourier transform look? This is again a sketch. This may not be the exact thing, but it starts at minus 2 omega m, and let me move it aside, this side of it. Yeah, like this, and you have 2 omega m here. So it will be a quadratic function. So it will be something like this. Okay, so this is just a representation. This is basically your x tilde of omega. So therefore, the maximum frequency in x tilde t is 2 times omega. So therefore, Nyquist rate is 2 times the maximum frequency, 2 times omega m. And 2 times omega m was the Nyquist rate of your x of t, that is omega naught, so this becomes 2 times omega naught. So when you convolve the signal with itself, your sampling frequency gets doubled. Okay, is it clear? Any questions?
No, ma'am.
Yeah. Okay, so let's move on to the fourth question then. So we'll spend some time in understanding this Nyquist rate business. It's important. It forms the basis of many future courses, including this digital signal processing, all of your communication courses if you are going to take them in your future semesters. Okay, so let's move on. Okay, so you have this so you have x1 of t with Nyquist rate as omega 1, which means the maximum frequency omega m1 as omega 1 by 2. And then you have another signal x2 of t with maximum frequency as Nyquist rate as omega 2, which means the maximum frequency as omega m2 as omega 2 by 2. Okay, so this is what you have, what you are given. And the first signal that we are interested in is y1 of t, which is x1 of t convolved with x2 of t. Okay, so we want to find the Knightley state of this particular signal. So let's say, so again taking Fourier transform, you have y1 of omega, which will be equal to the Fourier transform x1 of omega into x2 of omega. This comes from the convolution property. Of Fourier transform, and we want to find the maximum frequency of this particular signal. So now you are multiplying these two signals. So your ranges get changed based on who has the maximum frequency. I mean, whether omega 1 is larger or omega 1 is larger or omega 2 is larger. So the case we'll have two cases. So case 1 is when omega 1 is greater than omega 2, or omega m1 is greater than omega m. So what will happen? You have a signal. Just a moment, I think something happened. Sorry, let me again share the screen. So stay happening. Yeah, okay. So we have this. So we have omega m1 greater than omega m2. So let's say this is your x1 of omega. This is omega m1. This is omega minus omega m1. And then you have omega m. This is 0. And then you have your x of 2. Let's say it is something like this. Again, these are simple pictorial representations. This is omega m2, omega m2 minus, and this is your x2 of omega, and these two signals are getting multiplied. So the only region of interest, or that will survive, or that will be non-zero, is this. So this is the region of, or region where y1 of omega is not equal to 0. So therefore, the maximum frequency, let's say omega y1 is equal to omega m. Now you can have another case, that is your case 2, in which your omega 2 is greater. Omega 1 is less than omega 2, less than or equal to for that matter. So now what is the situation? You have your case like this, and this also translates to omega m1 less than or equal to omega m2. So now what you have your omega m1 something like this. So this is your x1 of omega. This is omega m1 minus omega m1. This is x1 of omega, and then you have something like this. This is omega m2 and minus omega m2. This is your x2 of omega. Okay. So now the region of interest is this. So highlighted one. So this is the region where y1 of omega is not equal to 0, and for this particular region the maximum frequency omega y1 is omega m1. So what is happening here? Let us see. So what is happening? in both of these cases, when omega y1 is what? Here it picks up the minimum of omega m1 and omega m2, and here again your omega 1 was less, omega m1 was less than your omega m2, so therefore this it again picks up the minimum of omega m1 and omega m2. So therefore your omega y1 is equal to minimum of your omega m1 and omega m2. Therefore the Nyquist rate is 2 times omega y1, which is equal to 2 times minimum of omega m1 omega m2. This 2 I can send inside, and therefore this will be equal to minimum of 2 times omega m1, which is omega 1, and 2 times omega m2, that is omega. So if you have convolution in time domain, in frequency domain you get multiplication and the Nyquist rate will be minimum of these two. Okay. Now instead of having convolution in time domain, if you have multiplication in time frequency, multiplication in time domain, that is y1 of t, y2 of t is x1t into x2 of t. So that will give me y2 of omega as 1 over 2 pi into x1 of omega convolved with x2 of omega. We have seen this multiple times, but still this is multiplication in time property. Okay, now we know that the maximum frequency is omega m1 and maximum frequency in this is omega m2. So your x1 of t, or rather your x1 of omega, is not equal to 0 in the range minus omega m1 to omega m1, and x2 of omega is not equal to 0 in the range minus omega 2 to omega m2. Okay, so this we know. Now there is a property of convolution which says that if you have one signal which lies between these two values, or let me just write it. So it says that you are interested in y of t, which is let's say you are interested in some signal z of t, which is z1 of t convolved with z2 of t. z1 of t lies only for t in a to b, and this lies only or non-zero only in c to d. Then the z of t will be non-zero only for values of t which are equal to a plus c and b plus t. This you can take up as a property. You can easily check it using convolution basic formula. We actually saw that for this particular question. So when your first signal lied between minus omega m to omega m, and the second signal also was between minus omega m to omega m, the convolution was between minus omega m plus omega m, that is minus 2 omega m, and till omega equal to omega m plus omega m, that is 2 times omega m. Same thing, but now you are having it in a more specifics. So therefore your y2 of omega is non-zero in the range minus omega m1 minus omega m2. So this I can write as minus omega m1 plus omega m2 to omega m1 plus omega m. So therefore maximum frequency that is omega y2 is omega m1 plus omega m2. Therefore, the Nyquist frequency is 2 times omega y2, which is 2 times omega m1 plus 2 times omega m2, which is equal to 2 omega 1, sorry, 2 times omega m1 is omega 1 plus omega. Okay. Any questions? If not, then let's move on to the fifth question for today. So the fifth question here says that you have x of t, which is equal to a when your t is in the range of minus 10 to 10. And your x of t has a continuous time Fourier transform as x of omega. Okay. And how does your x of omega look? We have seen this in earlier classes. This will be equal to 2a sine of 10 omega by omega. Okay. You have seen this multiple times. And how does your x of t look? Basically, your x of t is 1a from minus 10 to 10, and it is equal to 0, otherwise it looks something like this. So now what you are, then it said that you have y of t equal to x of t convolved with capital X of t, and you want to find the Nyquist frequency or its minimum sampling frequency of your signal y of t. Okay, so then you will have y of omega equal to Fourier transform of x of t into Fourier transform of capital X of t. Fourier transform of little x of t is x of omega, and Fourier transform of capital X of t will be given by 2 pi into little x of minus omega. This comes from duality property of Fourier transform. Okay, so what you have 2 pi capital X of omega into little x of minus omega. Now if you observe, this x of t is an even function. Since it is an even function, x of omega is equal to minus x of omega. So this is nothing but 2 pi x of capital X of omega into little x of omega. Okay, so how does it look? So we have y of omega is equal to 2 pi capital X of omega into x of little x of omega. Now this is basically some form of sinc function, which means that it is valid from omega ranging from minus infinity to infinity. So it is having non-zero values for frequencies that range from minus infinity to infinity. But this x of omega is non-zero only for a fixed value of omega. It is non-zero only for omega in minus 10 to 10. So this is non-zero only for omega in the range of minus 10 to 10. Okay, which means that this y of omega, since this little x of omega is limited in minus 10 to 10, this y of omega will also be limited in the range of for the values of omega in the range of minus 10 to 10. Else y of omega is 0. So therefore what do we get? So therefore the maximum frequency is omega y is 10. So therefore the Nyquist rate is 2 omega y, that is 20 radians per second. Okay. Any questions? Okay, let's move on to the next question then. So this question says that you have a signal x of t, which is cos of 100 pi t plus cos of 200 pi t plus cos of 500 pi t plus cos of 1000 pi t. These are sampled at a sampling frequency of 700 pi, and after sampling it is passed through a filter with cutoff frequency 600 pi. Now what we want to find out is the frequencies that are present in the resulting signal. Such kind of question has been asked multiple times in GATE. So let's try to see what exactly is the signal. So now what is happening? You have this x of omega. So we are sampling it at the frequency of um, sampling frequency of 700 pi. Okay, so x of t, let's say it has a Fourier transform of capital X of omega, and since these are sinusoids, cosines, so we know the Fourier transform that will be equal to impulses that are located at plus minus of the frequencies. So omega minus 100 pi plus delta omega plus 100 pi plus you have pi delta omega minus 200 pi plus delta omega plus 200 pi plus you have pi delta omega minus 500 pi plus delta omega plus 500 pi, and finally you have one more at 1000 pi. So pi times delta omega minus 1000 pi plus delta omega plus 1000 pi. Okay, so we have this. Okay, so this is what we have now. So let us first draw the Fourier transform of this signal. Okay, yeah, I am interested in till 2000. So we have 1000 here, 1000 minus pi, pi, minus 2000 pi. So then I'll have this is 500 pi, 100, 200, 300, 400, 600, 700, 800, 600, 700, 800, 900. So this is 100 pi, 200 pi, 300 pi, 400 pi, 600 pi, 700 pi, 800 pi, 900 pi. Then we have here 1, 2, 3, 4. This is 1100 pi, 1200 pi, 1300, 1400, 1500 pi, 1600, 1700, 1800 pi, and 1900 pi. And same way we'll have in the negative axis as well. I'm not drawing that for now. Let's just, yeah, I'm not drawing it for now. So what do we have here? You have x of omega, in which you will have, okay, let's draw it. It's okay. Minus 100 pi, minus 200, minus 300. I'm not writing pi here, assume it's there. Minus 700, minus 800, and minus 900 pi. And you have minus 1500 pi, sorry, 1100, minus 1200, minus 1300, minus 1400, minus 1500, minus 1600, minus 1700, minus 1800 pi, minus 1900 pi, and you have 2000. So now you have the first thing, the first value, you have an impulse at 100 and minus 100. So you have an impulse at 100 and minus 100. I'm not writing its magnitude. Then you have at 200 and minus 200 pi. Then you have at 500 and minus 500 pi. And then you have at 1000 and minus 1000 pi. Okay, so this is how you have. Now this particular signal, so this is your x of omega. Now this particular signal is sampled. It is sampled at a frequency 1600 pi. Okay. So now when you sample at 1600 pi, you get xs of omega, and xs of omega is basically summation with some scaling of k running from minus infinity to infinity x of omega minus k times omega s. So at every integer multiple of your sampling frequency, omega s is what? 700 pi. At every integer multiple of 700 pi, you will start getting replicas of this entire thing. So it will get shifted to 700, 1400, 2100, 2800, and so on. Okay, so the first replica that you will see will be at 700 pi. So here, this is your omega. So this is your omega s. This is your 2 times omega s. This is omega s. This is 2 times omega s. Similarly, here you will have minus omega s. So there will be replicas in both the directions. So I am not going to draw all. When you are at 700, you will get 7. So this will be at 700. So you will now start seeing peaks at 700 minus plus 100, minus plus 200, minus plus 500, and so on. So 700 minus 100, that will give you a peak at 600 and 800. Then you will also get a peak at 500, that comes from your 200 thing, and 900. Then another frequency you have is 500. So 700 minus 500 is your 200, and 700 plus 500 is 1200. And then you have 1000. So 700 minus 1000, you will get a peak at minus 300. And 700 plus 1000, you will get a peak at 1700. Okay, so this is what you have right now. Again, there will be a peak that comes from minus 700 that will be located here, like this. So from here you will get like this. Minus 1200 and at minus 1700, like this. Then the second one will be at 1400. So 1400 minus plus minus 100 is here. Then 1400 plus minus 2 is here. 1400 plus minus 500 will give you peaks at 1400, 900, and yeah, here. And 1400 minus 1000, you will get a peak at 400. And plus there. And similar replicas will also be there in the negative axis. I am not drawing that for now. Okay, so now what do you have? Then another one will be at 2100. When 2100 minus, you will get more replicas. More replicas. I am not drawing that. Integer multiple of omega s. I am not drawing that because we are not interested in all the replicas. Why? Because after sampling, this particular signal is passed through a low pass filter with cutoff frequency 600 pi. So the cutoff frequency is 600 pi, which is something like this. It is going to pass your 600. It's an ideal filter. So this is what you have. Okay. So what all frequencies are present now? So the frequencies that are present are 100 pi, 200 pi, 300 pi, 400 pi, and 600 pi. So final frequencies are 100 pi, 200 pi, 300 pi, 400 pi, 500 pi, and 600 pi. So these questions are going to come in your GATE exams. These are standard questions that generally come. Just a moment. Okay. Okay. So any questions till now? If not, then I'll move on to the next. Okay. Let's move on to the next question then. Before that, just give me a moment. So now again I will switch gears, and now we'll move on to the new concept that we discussed, and that was finding Fourier series coefficients or discrete Fourier series coefficients. So the first question here says that find the Fourier series coefficients for the x of n given to us here. So if you observe carefully, your x of n starts, let's say, at n equal to 0. Then it goes on till n equal to 5, and it repeats at 6. It starts repeating at 6. So x of n starts repeating at n equal to 6. So therefore the fundamental period n naught is equal to 6, and therefore your fundamental angular frequency is 2 pi by n naught, which is 2 pi by 6, which is pi by 3. So therefore Ck is 1 over n naught summation n running from 0 to n naught minus 1 x of n into e power minus j k omega naught, this is capital omega, sorry, omega naught n. Okay. So therefore Ck is equal to 1 by n naught is 6, summation n running from 0 to 5 xn into e power minus j k pi by 3 into n. Now the only three values are non-zero. So for n equal to 0, 1 and 2, it is non-zero. Otherwise, it is 0 in a given period, or rather the period of our interest. So therefore, Ck is 1 by 6. X of 0 is 1 into e power 0. plus x of 1 is 1 into e power minus j k pi by 3 n equal to 1, and you have x of 2 is 1 e power minus j k 2 pi by 3, and otherwise it is 0. Now I'll try to simplify this further. To do that, what I'll do, I'll take pi by 2 common from the second two, the last two terms. So e power minus j pi by 2 k, and that will leave me with e power j k pi by 6 plus e power minus j k pi by 6. Okay. Now I can multiply and divide by 2. That will give me 1 by 6 into 1 plus e power minus j k pi by 2 into 2 times cos of k pi by 6. Okay, now let us try to simplify this particular thing. E power minus j k pi by 2. I can write this as e power minus j pi by 2 whole to the power k, which is equal to cos pi by 2 minus j times sin pi by 2 whole to the power k. Cos pi by 2 is 0 and sin pi by 2 is 1. So this will give me minus j to the power k. So what I am left with is ck is equal to 1 by 6, 1 plus minus j to the power k into 2 times cos of pi by 6k. So these are the Fourier series coefficients, and this k is for what? This k is only for 0, 1, 2 and so on till n naught minus 1, n naught is 6, so 5. After that it starts repeating. Okay. Okay. Okay, if no questions, then let's move on to the next one. So the next question here says that again we need to find the Fourier series coefficients for this one. So for x, so yeah, so again your x of, let's say your period starts at n equal to 0. We see that it starts repeating at n equal to n equal to 4. So your fundamental period is n naught equal to 4, which means that your omega naught comes out to be equal to 2 pi by 4 or pi by 2. So therefore your ck's are now 1 by n naught, that is 1 by 4 summation k running from, sorry, n running from 0 to n naught minus 1, 4 minus 1, that is 3, x of n into e power minus j k omega naught is pi by 2, this is capital N. Okay, now this again I can expand. 4, I can write this ck as 1 by 4 x of 0 into e power 0 plus x of 1 into e power minus j k pi by 2 plus x of 2 into e power minus j k pi plus x of 3 into e power minus j k 3 pi by 2. Now here x of 0 is what? X of 0 is 3, x of 1 is 2 and x of 2 is 1 and x of 3 is 0. So we get 3 plus 2 times e power minus j k pi by 2. We have just seen in the previous question that it is minus j to the power k plus your x of 2 is 1. So 1 into e power minus j k pi, that is equal to minus 1 to the power k, and this is for k equal to 0, 1 and so on. Sorry, 1, 2 and 3. Okay, is it clear? Okay. Okay. So now let's move on to the ninth question. This is also like all the questions that like ninth and 10th question, both all are related to Fourier series coefficients. Yeah. Okay. So what do we have here? It is given to us that x of n is equal to e power n for n equal to 0, 1, 2 and 3, and we want to find the Fourier series if it repeats after every fourth instant. So the signal given to us is something like this. Say 0, 1, 2, 3, 4, 5, 6, 7, 8 and so on, minus 1 and so on. So you have e power 0 as 1, then you will have e square and e cube, and then it will start repeating. And so on. Okay, so this is what we have, and here also it will repeat e to the power 3. So again, if it repeats after every fourth instant, then the fundamental period n naught is 4. So therefore, omega naught comes out to be equal to 2 pi by n naught, that is pi by 2. Okay, so therefore your Ck is equal to 1 by n naught summation n running from 0 to 3 x of n into e power minus jk pi by 2 n. Again, we have the same thing. We have 1 by 4 x of 0 plus x of 1 into e power minus jk pi by 2 plus x of 2 into e power minus jk pi and plus x of 3 into e power minus jk 3 pi by. So this is equal to 1 by 4. E power x of 0 is 1, x of 1 is e, and this is minus j to the power k, plus we have e square into minus 1 to the power k, plus you have x of 3, that is e cube, and e power minus j k 3 pi by 2 is so you can see this as, so you have e power minus jk 3 pi by 2. You can write this as e power minus j 3 pi by 2 whole to the power k, that is equal to cos 3 pi by 2 minus j times sine 3 pi by 2 whole to the power k. Cos 3 pi by 2 is 0, minus j into sine 3 pi by 2 is minus 1 to the power k. So this comes out to be equal to j power k. So this comes out to be equal to j to the power k. And these are your sequence. Again, this is for k in 0, 1, 2 and 3, and after that it repeats. It's valid, it just repeats. This is the unique range. After and before it will just start repeating. Okay. questions, then let me move on to the next one. Okay, so the okay, so the what you have now is x of n is equal to 1 1 1 1. Let's say this starts from 0, and y of n is x of n convolved with x of n or itself. If y1 of n, sorry, not t, if y1 of n is y of n repeated after every 10th sample, calculate the Fourier series coefficients. Okay, so first of all, what do we have? We have y of n that is related to, so we have y1 of n that is related to your y of n, and y of n is what? X of n convolved with x of n itself. So this is nothing but summation k running from minus infinity to infinity x of k, x of n minus k. This is discrete time convolution, and we need to find this y of n. So first of all, you have your x of k, that is 1 1 1 1, so 0 1 2 3, and then you will have your 0 minus 1 minus 2 minus 3. This is your x of minus k. So this is when your n is equal to 0. Now if your n is less than 1, so or basically when you shift this particular signal to left side, there won't be any overlap. So the overlapping basically starts from n equal to 0. So for n equal to 0, your y of 0 is basically this into this, that is equal to 1. Now if you shift your signal by 1 unit rightwards, that is, if you look at x of 1 minus k, you get something like this: 1 0 minus 1 minus 2. So now you have two overlaps. So this particular thing is for n equal to 1. So you'll have y of 1 equal to, you have 1 into 1, so that comes out to be equal to 1 into 1 plus 1 into 1, that comes out to be equal to. Okay, let me just copy paste this. Yeah, so you have this, and one second. Yeah, okay. So now you will shift it by one more unit. So you will get something like this. So this is for n equal to 2. So you get y of 2 as you get 3 overlaps, 1, 1, 1. So that will give you 3. Similarly, if you shift it further, so this is 4. So sorry, 3, not 4. So y of 3 comes out to be equal to, you have complete overlap. So this comes out to be equal to 4. Then if you shift it further, that is when you have, this is for n equal to 3, now you have n equal to 4. Now you will start seeing less number of overlaps. So this is 1, 2, 3, 4, this is 0. Now the overlap is only for these three values. So again your y of 4 is 3. Now if you again shift it by 1 unit, so n equal to 5, you will now have overlap at these locations. That is 2, 3, 4, 5. So you have 2 and 3. So y of 5 is 2. Now you want n equal to 6. So n equal to 6, you will now have your things will start from 3. So 3, 4, 5, 6. So your y of 6 will have only one overlap, that is equal to 1. And for n equal to 7, your things will start from n equal to 4. And now for n greater than or equal to 7, there won't be any overlap. So how does your y of n look? Your y of n is basically equal to 1, 2, 3, 4, 3, 2, 1, and this starts from 0. Or if we sketch it, it will look something like this. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so your y of n is 1 for n equal to 0. Then it becomes 2. So this is 1, 2. Then at 2 it is 3. At 3 it becomes 4. Then it is 4. At 5 it is again 2. And at 6 it is again 1. So this is how it looks. And this is basically your y of n. But now what is given to us is your y1 of n. Your y1 of n is yn repeated at every 10th sample or 10th instant. So 10th instant means at n equal to 10, it starts to repeat something like this. And so on. And otherwise it is 0 here, so 0 here, and again at 20 it will start repeating, and so on. And similarly in the negative side also it will start repeating. So what do we see? So your y1 of n is a periodic signal with period, fundamental period, and not equal to 10. Omega naught is 2 pi by 10, that is pi by 5. Okay, so this is what we have. And in the period where n belongs to 0 to 10, y1 of n is is equal to y of n. So this is what we just saw. Okay. So now we want to find out the Fourier series coefficients of this. So this y1 of n, let's say it has the Fourier series coefficients as ck. So therefore this ck will be equal to 1 over n naught is 10, summation n running from 0 to n naught minus 1, n naught is 10, so 9, y1 of n into e power minus j k omega naught is pi by 5 n. Okay, so this becomes 1 by 10, and in this particular period from 0 to 9, y1 of n is basically y of n e power minus j k pi by 5 n. Now again I can separate these things, so I'll get y of 0 plus y of 1 into e power minus j k pi by 5 plus y of 2 into e power minus j k 2 pi by 5 plus y of 3 into e power minus j k 3 pi by 5 plus y of 4 into e power minus j k 4 pi by 5 plus y of 5 into e power minus j k 5 pi by 5 plus we have y of 6 into e power minus j k 6 pi by 5, and y of 7, y of 8 and y of 9 are 0. So we can simply ignore them. So we have this now. Let us substitute the value of y of k now. This is 1 by 10. So y of 0 is 1. So this becomes 1 plus y of 1 is 2 into e power minus j k pi by 5. Y of 2 is 3 into e power minus j k 2 pi by 5. Y of 3 is 4 into e power minus j k 3 pi by 5. Y of 4 is again 3 into e power minus j k 4 pi by 5 plus y of 5 is 2, 2 into e power minus j k 5 pi by 5 plus y of 6 is again 1. So e power minus j k 6 pi by 5. Now in order to simplify this further, what I do, I take this e power minus j k 3 pi by 5, which is the middle term or the center term, outside. I'll just take this complex exponential outside, common. I won't touch the other things. So this will give me e power minus j k 3 pi by 5 divided by 10. Inside the bracket, I'll get e power j k 3 pi by 5 plus 2 times e power j k 2 pi by 5 plus 3 times e power j k pi by 5 plus 4 plus 3 times e power minus j k pi by 5 plus 2 times e power minus j k 2 pi by 5 plus e power minus j k 3 pi by 5. Okay. So this is what we get. Now we'll combine the terms which have same coefficients. So that will give me e power minus j k 3 pi by 5 by 10. Inside the bracket, I'll get the first term will be e power j k 3 pi by 5 plus e power minus j k 3 pi by 5. The second term will be 2 times e power j k 2 pi by 5 plus e power minus j k 2 pi by 5. The third term will be 3 times e power j k pi by 5 plus e power minus j k pi by 5, and the last term is this 4 as it is. is what we have. Now at every term I can multiply and divide by 2. So that will give me, let me add a page. So that will basically give me e power minus 3, 3 pi by 5k plus 4 times cos of 2 pi by 5k plus 6 times cos of pi by 5k plus 4. And I can write this 10 as 5 into 2. That will cancel out these terms. So that will basically give me 1 ck to be equal to 1 by 5 into e power minus jk 3 pi by 5. Inside the bracket I have cos of 3 pi by 5k plus 2 times cos of 2 pi by 5k plus 3 times cos of pi by 5k plus 2. So these are the discrete time Fourier series coefficients for this particular given signal, simplified form. And again, this k, the unique range of k will be from 0 to 9. And after that it will start repeating. It's there, it just repeats, that's all. Okay, so this is all about this particular question. If you have any queries, then please let me know. Okay, so this is all I wanted to cover for today. If you have any questions, then please let me know in any part of today's tutorial. Otherwise, you are free to leave the meeting. Thank you for attending today's session.
Thank you.
Yeah, thank you.